Hello viewers, myself T. Oza here. In this new video, we will discuss about NMR of some less commonly used nuclei like nitrogen, fluorine, silicon and phosphorus. So let us proceed one by one. This video briefly discusses the NMR spectrometry of some isotopes other than the most common one, that is H1 and carbon-13. These include 15 nitrogen, 19 fluorine, 29 silicon and 31 phosphorus. Two of these elements, that is nitrogen and phosphorus, are of extreme biological importance, including MRI, while all these are pivotal in synthetic organic compounds as well as inorganic compounds. Like 1H and 13C, these four are spin half nuclei having spherical shape and spin angular momentum vector I given as follows: I equal to under root of I into I plus 1 whole multiplied by H upon 2 pi equals 0.866 H cross. Let us proceed with the introduction part. These spin half nuclides do not possess electric quadrupole moment. Of these four, fluorine and phosphorus are monoisotopic, that is 100% natural abundance. The natural abundance of nitrogen 15 is very low, 0.36% compared to nitrogen 14, which is more than 99%. And that of silicon is 4.7%. Secondly, the relative sensitivities compared with one for hydrogen. Here these are 1.04 into 10 to the power minus 3, 0.83, 7.84 into 10 to the power minus 3, and 6.63 into 10 to the power minus 2, respectively for nitrogen, fluorine, silicon, and phosphorus. At about 7 Tesla magnetic field, their resonance frequencies are in the vicinity of 300 MHz for fluorine, 21.67 MHz for nitrogen 15, 60 MHz for silicon 29, and 121 MHz for phosphorus. Whereas N-15 absorptions are referenced by pressurized ammonia liquid as external standard. Formerly, ammonium nitrate or diazomethane or methyl nitrite or nitric acid were used. The fluorine NMR spectra are referenced by CFCl3, silicon by TMS, phosphorus by 85% phosphoric acid in water as external standard. The delta ppm range of 15 N, 19 fluorine, 29 silicon and 31 PR, 1100 to minus 400, 276 to minus 280, 80 to minus 380, and 270 to minus 480 in that order, means nitrogen, fluorine, silicon and phosphorus. The following figure, adapted with thanks, shows the spectrum of urea. Note the broad peak of 14 N and the sharp peak of 15 N. The magnetogyric ratio of 15 nitrogen is very small and negative, minus 2712 as compared to plus 26753 for hydrogen. G factor is 0.566. Magnetic moment is also very small and negative, 0.283 nuclear magneton, and NMR frequency is 4.315 MHz per Tesla. The chemical shift data are very much erratic, hence assignment becomes difficult and challenging. The 1H decoupled nitrogen 15 NMR spectra of formamide in CDCl3 occurs at 113 ppm. The nitrogen atom in formamide has partial double bond character hence it gets shielded. And by shielded means higher magnetic field value for delta ppm. The 15N NMR absorption of ethylene diamine shows peak at 12.5 ppm because in this case the nitrogen atom is shielded as compared to formamide. The proton coupled spectrum shows a quintet. Diisopropylamine resonates at 72 ppm and pyridine at 214 ppm. The quinoline ring has two nitrogen atoms. One is unsaturated, the second one is saturated. They resonate at 300 ppm for unsaturated and 30 ppm for the saturated one. The structure of the molecule is shown, adapted with thanks. You know this alkaloid is found in quinine, in cinchona plant. Despite the absence of clear-cut generalization regarding the chemical shift data, 15 nitrogen NMR studies are being strenuously pursued in biochemistry and pharmaceutics, in medical sciences. Specialized techniques are used to prepare 15N enriched samples for NMR studies. 15N enriched proteins can be prepared by feeding plants such enriched precursors. The 15 nitrogen NMR spectroscopy is being used in the study of biogenesis of natural products, drug metabolism, and also in medical diagnostics, MRI. Next, we pass on to silicon-29 NMR. The NMR parameters of silicon-29 are spin quantum number high equal to half, natural abundance 4.7%, sensitivity related to 1 for H 7.85 into 10 to the power minus 3, absolute value 3.69 into 10 to the power minus 4, magnetic moment minus 0.5555 nuclear magneton, gyromagnetic ratio minus 5319, which is about that of carbon. For carbon it is positive 6728. NMR frequency megahertz per Tesla is 8.458. The ppm range is plus 50 to minus 200. Like fluorine, silicon is not found in natural organic compounds. However, both occur in countless synthetic compounds, particularly in polymers and silicon oils. U1S decoupled silicon-29 NMR spectrum of TMS shows a sharp singlet positioned at 0 ppm, whereas the proton-coupled spectrum results into a 13-line multiplet caused by 12 equivalent protons. All lines may not be visualized. The spectrum of trimethylsilane shows a sharp line at about 0.3 ppm, while the proton-coupled spectrum shows two multiplets separated by 175 Hz, the one bond coupling constant. The 29 silicon NMR spectrum of ET2, SIH ET2 shows a singlet at about minus 5 ppm, while the proton coupled spectrum is a doublet, further split into a doublet of 5 lines each. Obviously, one bond splitting by SIH gives a doublet. Two bond splitting by CH2 groups gives a quintet, which is further split by 13C and methyl hydrogens. But these are too small splittings, hardly resolvable. Silicon NMR method is useful in the study of rocks, meteorites, silicon oils, polymers, and also in environmental pollution. Next, we pass on to 13-1 phosphorus NMR spectrometry. NMR parameters of phosphorus 31. Spin quantum number half, natural abundance 100%, relative sensitivity 6.64 into 10 to the power minus 2, gyromagnetic ratio 10,840, nearly twice that of carbon 13, which is 6728, G factor 2.261, magnetic moment 1.1005 nuclear magneton, NMR frequency 17.236 per Tesla. The element phosphorus is very important biologically. It occurs widely in several organic and inorganic reagents and in synthetic compounds, insecticides, polymers, pharmaceuticals, medical diagnostic reagents. Examples include phosphines, phosphite esters, ylides, phosphate glasses, adenosine diphosphate, adenosine triphosphate, nucleic acids, phospholipids, etc. In view of this, phosphorus NMR has been extensively studied. We shall take a few examples. 31P NMR of phosphoric acid in water is used for referencing the peaks. It gives a singlet which is positioned at 0 ppm. Another example is diethyl chlorophosphate, CH2, CH3, CH2 twice, POCl. Whereas the proton decoupled 31P spectrum is a singlet at 5 ppm. The coupled spectrum is a quintet split by CH2 hydrogens. It may be noted that the methylene hydrogens in diethyl chlorophosphate are distereotopic, as is shown by the appearance of its 1H spectrum, giving a triplet of doublets for the methyl hydrogens. The reagent triphenylphosphine shows a singlet peak for 31P. Next, we pass on to the fourth element, fluorine 19, which has 100% natural occurrence, monoisotopic. The parameters are quantum number is quantum number half, sensitivity quite high, 0.83, relative to 1 for hydrogen. Gyromagnetic ratio is also high, 25,179. G value is 5.255. Magnetic moment quite close to proton, 2.63 nuclear magneton. For 1H it is 2.79. NMR frequency is 40.055 MHz per Tesla. For proton it is 42.76 MHz. Chemical shift range 276 to -280 ppm. Reference compound CFCl3. Preferred solvent CdCl3. Fluorine containing drugs can be studied by high magnetic field. Fluorine 19 NMR studies. An interesting example is that of parafluoroacetophenone. This compound represents an example of A prime MM' X spin system for the protons. A and A prime refer to protons on carbon 2 and 6. M and M prime refer to protons on carbon 3 and 5. X refers to fluorine atom. The decoupled spectrum is a sharp line at about -102 ppm, whereas the 1H coupled spectrum shows a complex multiplet. A similar case is parafluoronitrobenzene. The structure of parafluoroacetophenone is shown here. Another example is that of fluoroacetone, CH3, CO, CH2F. Its 1S decoupled spectrum shows a singlet at -230 ppm. The proton coupled spectrum shows high J value and low J value triplet. So in this way, we have briefly discussed the spectra of fluorine 19, silicon 29, phosphorus 31, and nitrogen 15. The basic principles remain the same as for carbon 13 and proton. However, some differences are there, particularly the sensitivity of the three other than fluorine is very low, so special techniques are required. Secondly, the chemical shift values are mostly erratic. The care has to be taken for their assignment. One more point I would like to discuss. In some cases, the gyromagnetic ratio is given negative sign. In some cases, it is given positive sign. So these are presented here pictorially. By positive sign, we means clockwise spinning, clockwise precession. By negative sign, we mean anti-clockwise precession of the nuclear magnetic moment along the z-axis of the magnetic field. Now for practice, given below are three spectra. The compounds are noted. The multiplicities are shown. What we have to do, we have to analyze the spectrum for 2 points. Firstly, what are the factors which are affecting chemical shift? And thirdly, how is the multiplet originated? So these will be very useful for understanding purpose. Spectra number 1 here, spectra number 2 again for silicon, and spectra number 3 of phosphorus compound. For practice, we should do this. Thank you very much, viewers. Please do like, share and subscribe my channel. Thank you very much. Once again, thank you.